Here it is, the perfect mechanical wave, over 1 metre high, and you get one every minute of these. Now the science on display here could be changing the nature of surfing. So how does it all work? I'm with Alex, the engineer, so tell us.
Okay, it's very simple. It's just the foil that moves underwater, and with the lagoon shape, we are able to create perfect waves.
Every time?
Every time.
For as long as you like?
Yes, we have a powered run here of 150 meters, but we can build as long as we want. Okay, so this is the control panel. We have information here that shows the height of the wave, the speed of the wave, and every parameter that, from an engineering point of view, it's critical for the functioning of the machinery.
And you just start it by pressing that red button?
Yeah, and just stop it pressing another button.
So I've surfed a bit at home. I've never tried anything like this. I'm going to give it a go.
Any surfers here? I've surfed a long time ago. So this is a human-made surfing pool, like a big wave pool, I guess, with a perfect wave. You can engineer the wave in something. It's kind of interesting.
Really good, really fun. A lot more powerful than I thought it would be. A lot steeper. It's quite weird paddling kind of towards the pontoon. And normally when you're out in the ocean, you can see the wave building behind you and it suddenly comes up from nowhere. But
anyway, so what else we got? This one didn't seem to play.
Watch closely. This is Britain's Andrew Cotton harnessing a monster wave that could be the biggest ever ridden. He held his position for 10 seconds in an attempt to enter the record books.
I'm sort of very focused on what I want to do and where I want to be on the wave. I actually want to surf the wave. I just don't want to like hurtle down out of control. You know, when you're doing things like this, it's fine line with things are surfable and safe and dangerous. And then 4 hour session and we only caught a wave each. It's not ideal, but you know that's just how it is.
See it again, and the size of the wave hits you. Andrew rides at 80 feet. That's higher than the Angel of the North and nearly half the height of Nelson's Column. The current surfing record of 78 feet is held by Garrett McNamara, seen here off the coast of Ireland with Andrew Cotton last year.
The mission is to surf the biggest wave in the world. And very luckily, I haven't actually been doing.
Mute it, and we'll do some things. All right. If you couldn't work out, we'll talk a little bit about waves today. Any business we need to take care of before we get rolling? So you might have gathered from what we've just looked at today that our plan is to look at 3 things today. We'll look at waves, we'll look at viscosity of fluids, we'll look at surface tension, and in between those we'll come back and look at the phase behavior of different fluids, liquids going to gases and so forth. And so that's our plan for today. Let me get arranged so we can do that. You recall from last time the things we talked about. I won't go through in great detail. We talked about definitions for different components. We talked about definitions for modulus, for density. We didn't talk about viscosity. And we talked about pressures and temperatures for phase behavior. We talked about equations of state and defined through the ideal gas law, and talked about isothermal and isentropic expansion, and so how to relate those. And we talked briefly about compressibility, as we've talked this morning, either in terms of a volume change as you apply a pressure or a density change. Obviously, if there's a volume change and you keep the same mass in it, then there has to be, by definition, a change in density, because density is defined as mass per unit volume. Probably the most important thing we talked about last time was dimensional homogeneity. The fact that if you're adding apples, you have to add them to apples. So all the units in a single equation must be the same if you're adding them to each other. and we talked specifically about Bernoulli's equation, and we played around a little bit to show you how you could actually get the units out of equations that you didn't know. So for instance, if you want to know what the units of force are, you know they're newtons, but if you wanted to know them in terms of mass, length, and time, which for us will be kilograms, meters, and seconds, then to do that, we can just define forces as a function of things that we know, such as mass and acceleration. Mass is kilograms, accelerations is meters per second squared. So by definition, you have the units in terms of mass, length, and time for those. And so that'll be important for us as we go forward. So we'll take these things now and we'll expand, I guess, on the properties that we now define. We said something a little bit about waves last time in terms of wave speeds. We talked about the Froude number, and we'll come back to that. We'll talk about viscosity, how viscosity controls the rates at which fluids flow. We'll explore how liquids turn into gases and over what ranges in terms of liquids turning into gases in terms of vaporization. And we'll talk about interfacial tension or surface tension, all of which are important features. So the first topic are wave speeds. So we looked at some videos showing behaviors in terms of wave speeds. And so we can think of waves in a variety of different ways. If I hit this table, and if you had your ear on the end of the table, you would feel the wave traveling along that table and hitting your head ultimately, kind of a bit like a line of train cars. You hit the end train car, boom, 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 boom. That's the wave that's traveling along to hit the one that's furthest away from the locomotive as it goes through. And so those are compressional waves that are present in solids. And the expression that defines that for travel of a compressional wave in either rock or air, if this shear modulus in liquids is equal to 0, then the compressional wave is estimated or approximated by the bulk modulus, which we just talked about, divided by density and square root. And so this is of interest to us because, well, apparently last night there was a magnitude 7 earthquake on the border between Bolivia and Brazil, I think. And the rate at which speed of that earthquake travels in the ground and the rate at which my voice reaches you are both governed by this expression. And so if we look at, for instance, the moduli of rock, modulus is something like, for rock, let's call it 2 times 10 to the 10 pascals, just a number that I know is about right. Density of rock is about 2,500 actually, 2 times 10 to the 3 kilograms. And so if you take those two together and calculate the wave speed for rock, it's going to be of the order of 2 times 10 to the 10 newtons per meter squared divided by something like 2 times 2,000 kilograms. And all by way of saying, if we get rid of these, a newton per meter squared, a newton is a kilogram, right? You know that 1 newton equals the force needed to give a mass of 1 kilogram, an acceleration of 1 meter per second squared. And so if you substitute for this, you end up with 10 to the 10 divided by 10 to the 3, which is 10 to the 7, which is 10 times 10 to the 6. it should be meters squared per second squared. And the square root of this is just something like 3 times 10 to the 3, which is 3,000 meters per second, which is about right. The conversion between meters a second to miles an hour is about 2. So this is about 6,000 miles per hour. So these conversions should be something, as an engineer, as becoming an engineer, are things that you should be able to do. I don't expect you to know all of these numbers, like this, for instance, but you should know that water is 1,000 kilograms per cubic meter. So you can make that. If you wanted to calculate this wave speed in water, you could do that just by substituting whatever the velocities and modulus is of water. Actually, the modulus of water is actually very similar to this. The density of water is perhaps a factor of 2 different, right? It's 1 times 10 to the 3. And so the acoustic velocity in water is something like, it's of the order of 1,000 meters per second, something of that order, or 1,500 maybe. And so you can calculate that. The speed of sound. So you're listening to me. So in air, what's that going to be? We said last time that surprisingly the modulus, it came from the ideal gas law, the modulus of air is equal to the pressure. We said that, where am I going to write it? E air is equal to the pressure, absolute pressure. Pressure in here is 100 kilopascals, or 10 to the 5 pascals. So this is 10 to the 5. Density of air is something like 1 kilogram per meter cubed. And so if you do this, you end up with, what is that? That's 10 times 10 to the 4, which is 300 meters per second, if you do this calculation. This is pascals. This is newtons per meter squared. And 300 meters per second is about 600 miles per hour if you multiply it by 2, which you know is about right. Planes fly about 600 miles an hour, commercial airliners. They're just under the speed of sound, maybe by 10 or 20%, because so you don't have to reinforce them to travel much faster, and so we can calculate what those are. So the speed at which waves are going as compressional waves, listening to me, listening to the end of this table, that is controlled by this. However, in fluid mechanics, that is only one of the kinds of wave speeds we worry about. Is that someone's phone? I could never work out whether it's my stuff going on in the background from my browser. But the celerity wave is the velocity of the wave as it travels on a surface. And so this is a different kind of wave. It's by rotation of the particles that are in here that get passed along here. This is the term that we would want to define. We actually defined it last time. You remember that we took Bernoulli's equation, or you might not. And what we did was we divided two terms by each other, two of the terms by each other, and we came up with what was a Froude number, which was equal to V over GZ in this term. So if you take these two terms, this one here, and you divide one by the other, you get a dimensionless number, which is the Froude number. And you'll notice that if you unpick this number, this is exactly what you get, which is the wave speed. And so this basically says that the speed of a surface disturbance is equal to this velocity, which is equal to gravitational acceleration times the depth of the water. And so if, for instance, this depth is of the order of 1,000 meters, which it might be, then we can calculate this. This is going to be 10 meters per second squared, 9.81, right? You know that. And if this is 1,000, then this is equal to 10 to the 4. This is in meters, so this is in meters squared per second squared, whole square root, which is about equal to 100 meters a second. So this is saying that a wave far out to sea, where it's quite deep, a kilometer deep, is traveling at 100 meters a second. And if we use this conversion of 2 to 1, it's about 200 miles an hour, which is surprising, right? And so the reason for this is that if you look at the Tohoku earthquake, the Great Eastern Japan earthquake of 2011, then what happened was that on the seabed, where you have the two plates, one plate undercutting the other plate, the strength of this is exceeded. All of a sudden, it lets go. There's a rupture that occurs along this boundary, this plate boundary, which was in this case something like 100 kilometers long along this trench that you see here. So this plate is diving down underneath Japan. And so this is kind of backwards from this figure. This is Japan here. This is the plate that's going underneath it. So it's flipped, if you like. This would be towards the US, and this would be towards Japan. So it's the opposite way from this north-south picture. And as this goes, you get exactly this override. All of a sudden you have a fault develop, you push up the seabed, maybe tens of meters, all the water above that goes up tens of meters, the stuff on the other side goes down, and you have this disturbance, a wave, that then travels as a solitary wave and travels onshore. And so the early warning systems for that are that because of these different wave speeds, we didn't really give any reason as to why we did this. If the wave speed is traveling at 3,000 meters a second in rock, then the time it takes to get to the shore is quite short compared to something traveling at a 30th of that speed. 100 meters a second versus 3,000 meters a second. So the early arrival of the shaking that occurs from the P waves will occur basically instantaneously, the same speed as a jet flying, actually much faster than a jet flying, right? 10 times as fast as a jet flying. And so will occur almost instantaneously. But if the other one's traveling at 100 meters a second, this distance from the trench to here is something of the order of 100 kilometers. And so 100 meters a second is 10 seconds to go a kilometer. So it's 1,000 seconds to go 100 kilometers. And so the wave is going to take something like 1,000 seconds to get on shore. 600 seconds is 10 minutes. And so it's about 15 minutes or so. And so what you can use, and it's true for other places as well, the idea of an early warning system. You have ocean bottom seismometers that sit on the trench. Shaking occurs. Actually, you don't have to wait for the wave, the damage to come on shore. You record the wave. You use AI to process, it's a big earthquake. You send that signal electronically, speed of light, not the speed of sound, to onshore. It alerts you on your radio, and it gives you the time for the seismic wave to travel 100 kilometers for you to get out of the building, which is of the order of maybe a minute. The damaging waves are the shear waves, not the P waves, the ones that are like a skipping rope moved on the ground, and those travel about half the speed as the P wave. And so that gives you maybe an extra minute. So maybe it gives you a minute. You have a radio in the building. This is actually in the building in Tohoku near Sendai, where this earthquake hit a year after the date. And that goes off, you go out of the building, and then you take care of yourself. If you're inland, you do no more. This is the damage that occurred in these buildings. They lost one building on campus. But the real problem from this event, as you know, was the tsunami that came. The tsunami is delayed because it travels at 100 meters a second, not 3,000 meters a second. And so we know that that's going to take something like 15 minutes to be able to come on shore. And so now if you know about that, you go onto higher ground and you avoid it. And you avoid, this used to be populated and was basically scraped off by the tsunami. This was 1 year later to the day the day before the event, and it was just rice fields filled with brine that had washed in, etc. Just completely devastated. And lots of very sad places. A high school with 4 stories where only the 4th story wasn't affected. The lower 3 were, and just a complete mess. And so what I will do now is, if we have this event, oh, I didn't want that actually at all, is if I can find the right, well, this is actually a funny one, right? Don't listen to RT for anything else other than these. This is a boat going out to sea at the beginning of this event. And the commentary is funny as So these are these solitary waves that are coming in. When they're far out to sea, they're very small. But in this case, they might be quite large because there's a big offset from the plates. But these are coming in. They slow down as they get closer in because it's shallower. And so it might not be traveling at 100 meters a second. It doesn't really look like it's traveling at 100 meters a second. And it comes on shore. And so the other thing that we'll do, if we have this, I won't do that. I won't do that. Won't do that. Do I not have it? Where is it? All right. This is exactly what I want. So let's start this going. So this is the event. I'll turn it on because I think that... So this is the event, the time that the event hits. And this is everyone fleeing up into a upper story of a parking garage. Boats going out to sea during the event. And so what I'll do is I will mute this. Yeah, you can hear that. Sirens going. But what we'll do is, this is immediately after the earthquake has hit. And so what we'll do is we'll keep that open in the top right-hand side, and we'll look at what happens at 5, 10, and 15 minutes in terms of what our predictions might be in terms of what's going on. So we'll do that. Okay. So we said we'd talk today about waves. That's probably all we need to say about waves. But the point is, the waves come in different forms. The P wave that hits this has a different expression from the celerity wave, which travels on the surface of a liquid. And we have to realize that they are slightly different. Viscosity. All right, let's move on. So I don't want this to be too fractured. Viscosity. Let me do this. Will it keep it on top? Oh, it does keep it on top. All right. All right. So where are we today? We are 1-3. So we're cleaning up the remaining material properties that we have to describe. So viscosity is a property, as you know. Syrups have very high viscosity. Water has a lower viscosity. Air has an even lower viscosity. The idea is if you put something on an inclined surface and let it move down the surface, the rate at which it will move is controlled by the viscosity. It's a relatively straightforward concept. It's governed by Newton's law of viscosity, which says this, which I'll explain with a figure. Someone wake me up actually by the time, hey Siri, set timer 5 minutes.
I wish I could help, but you don't seem to be connected to the internet.
Oh, we're not connected to the internet. Oh, forget it, Siri. Forget it. You're no good. 5 minutes and 30 seconds. Technology for you. So imagine that we take 2 plates that are parallel to each other. we take this upper plate and we move it at some velocity Vx. If we take a marker and mark between them at time 0, then all the points within this liquid between them would be arranged on this marker. If we move this plate so that it moves at some velocity, then if we assume that the fluid moves like a pack of cards, shearing a pack of cards, then the one which is attached to this upper plate, which is moving at this velocity Vx, would have traveled a given distance in a unit time, which would actually be equal to Vx. This would occur over some height between these, which we could call dy. And so the viscosity is defined as the force that we have to apply, shear stress, and shear stress tau is equal to a force that we apply tugging on this upper component divided by the area of this plate, the plan area of this plate, which we sheared against. And so, very simply speaking, the gradient of this, which is given by this little, oops, this is dy dv x. We should probably draw a coordinate system, right? This is the x coordinate, this is the y coordinate. So shearing this, the velocity that this goes, the fluid is attached to this static surface at the bottom, it's attached to this moving surface at the top, and everywhere between that just gets translated by a fraction of what the separation is between these two things. And so all this is an empirical law. It's Newton's law of viscosity. Which basically says that the shear stress or the force that you have to apply per unit area is proportional to the velocity that you move it at and the thickness of the gap between those two plates. And the coefficient that links those is the viscosity, which we'll call mu. And so if you were to draw this out on a figure, you would be able to plot this as shear stress, a seagull flying across that figure I see up here. And this is you could think of this as, this is the, well, d vy dx. You could think of this as the shear rate, if you like. In other words, how quickly it's shearing itself. And for a Newtonian fluid, it would look like this. Goes through the origin at 0. And if you apply a given stress tau 1, you immediately define a particular shear rate dv1. If you double this to give you twice that, if this is 2 times tau 1, then the consequence is, for this particular plot, is this will be 2 times that amount, whatever that is, right? And so this would be referred to as a Newtonian fluid. That's an F, that's a fluid. And so in other words, the shear stress is directly proportional to the shearing rate. There are other fluids that exist. I guess I can't move this window. Oh, yeah, I want to change the color of the pen, but apparently I can. There are other fluids, and other fluids that might be of interest to you, depending on what area you work in. These are non-Newtonian fluids, so only fluids that go through the origin and are linear are Newtonian fluids. All others are non-Newtonian fluids. And this type of fluid here would be called a thixotropic fluid. Can you read my handwriting, by the way? Thixotropic. And that's an important class of fluids because it includes, for instance, drilling muds. And it means that you have to apply, that's it, that's 5 minutes gone. Well, we can look at this, still no tsunami. Lots of stuff going on. Let's turn the volume on. Nothing apparently going on. Okay. I love this screen stuff. Well, except what I should have done was change my the color of my pen. So thixotropic fluids are ones where if you apply a shear stress of this magnitude to it, there's no velocity. You have to increase the shear stress, there's still no velocity. Only when you apply a threshold shear stress, and this would actually be called the yield stress, I guess. Do you start to be able to shear it? So it's important because it applies in muds, it applies force to the side of the hole. It doesn't actually circulate or move unless you get above some threshold value. And then as you start to increase the stresses, then you increase the stress, but you don't double with each time the magnitude of the shear stress that you apply. Well, you do actually, I guess, above this threshold. And so there are some examples, I guess. Maybe it's worthwhile just doing an example. We don't do so many examples in this class. Here's a very simple example that is trying to make this case. This is a thixotropic fluid. This is Newtonian fluid. And so this is an example that looks just at the very simple geometry and asks you to solve this question. So you have oil 1 and oil 2 that are separated by some plate. This plate is moved at some velocity, which is 0.3 of a meter a second. The upper surface is fixed. The lower surface is fixed. This is moving at some velocity, v0. And what's the question? Calculate what the viscosities are. That's the only thing you don't know. You know that the force that's applied to these is 29 newtons. So this is equal to 29 newtons. But you don't know what the viscosities of these oils are. mu1 you don't know. mu2 you don't know either, except you know that it's twice the viscosity of mu2. So how would you do that? Well, straightforwardly, you know that if this moves at some velocity here that you know, then the profile within this fluid is going to be this. This is V, just V. You know that the profile within here will be exactly the same because they have to move with the same velocity here. And you can write that the shear stress in fluid 1 is going to be equal to the viscosity of 1 multiplied by the change of velocity in the y direction, with the x direction, with y. And for fluid 2, it's going to be equal to mu2 times the change in velocity with the distance, dy. And you can start substituting in what the components are. You know that this here, this total amount here is dy. You know that this velocity here is 0.3 meters a second, as is this, because they have to be going at the same rate. If you know, I think in this case both of these separations are the same, so you know this. And you know that the total force acting on here has to be the sum of these two acting together. And so the main expression, which is given below, has to be that the total shear stress has to be tau 1 plus tau 2. You know that under here that this total shear stress is equal to 29, it's going to be 29 newtons over the area of the plate, which you must be given as well, so you know this. You know that each of these two components are given by this, and so you can rearrange this to be able, and you know that in this particular case, mu2 is equal to, come back to that in a second. We know that mu2 is equal to 2 times mu1. And so you can substitute this into here. And once you've put these together, you know that the left-hand side of tau is given by this, which you know. You know these velocities, which are 0.3 meters a second. You know the heights of these, which must be given, which is 0.03 of a meter, which is 3 centimeters, I guess, right? 3/100ths of a meter. And so the only unknown you have is mu1. And so you can solve for mu1. And if you do that, I think it's all given here. You can figure out exactly what it is. That you can work out that the ratio of these should be to, if you know what mu1 is, you know that mu2 is double that, and so you can figure it out. Okay? So I know we've gone through that very quickly, but it's certainly recorded, and so you can rationalize that. But merely the assumption is that all the things that we'll work in this class, you typically assume that there's a linear variation of the velocity from this fixed magnitude where it's attached to this static wall to this fixed magnitude where it's attached to the moving plate, which is moving at this given velocity, and it's really just like skipping a deck of cards. Okay? Where are we? This is still rolling. Well, you see something happening on the horizon. It should be 10 plus minutes now. You can see, actually it's 15 minutes on this if I see it properly, right? 15.3 minutes. You see something happening in the distance at the breakwater. Something's going on. This is a town called Kamaishi. It's on that east coast of Japan. It actually is kind of the Pittsburgh of Japan. It's where the steel industry went to after the Second World War when it moved offshore from Pittsburgh to Japan. After being in Japan, it went to Korea. After being in Korea, it went to China. And now I think it's not so much in China, it's more in Vietnam. It travels around the world. Okay, put that back, and I'll go back to this. Right. In terms of viscosities, viscosities typically, I guess, change for different materials. Two good numbers to remember. Typically, viscosity changes with temperature. If you look at a reasonable number for a liquid like water, a good number for a viscosity, a dynamic viscosity, is something like 10 to the minus 3 Pascal seconds. A good number for a gas is something like 10 to the minus 5 Pascal seconds. Don't need to remember those, but you can make yourself a very valuable employee somewhere down the road by knowing some numbers that allow you to know that at least the viscosity of a gas is twice as low as that for a typical liquid. That viscosities for liquids decrease as you warm them up. They get less viscous. But gases become more agitated and viscosities increase as you increase them. You increase temperature. You can see what's happening on the horizon. Okay. The behavior of liquids, we may run out of time. There's a phase diagram here. We talked about this a little bit the other day. But if you look at the behavior, the phase behavior of liquids, then we know that for water, at 1 atmosphere, the freezing point is 0 degrees Celsius. The boiling point is 100 degrees Celsius. You can change those. The boiling point just means that at that temperature and that pressure, the exchange of molecules going from the liquid state to the gaseous state exceeds the equilibrium exchange, which is what it is if there's same number of molecules changing form. If you reduce the pressure by some magnitude, it means that you can boil the liquid at a much lower temperature. So in other words, if you're at 20 degrees centigrade, I'm not sure where that would be on this graph here, it means that the boiling point for water is at some reduced atmosphere. So if you can reduce the pressure less than atmospheric, then you can cause it to boil even though it's not at a relatively cold temperature. And so that's what happens, for instance, on propellers on ships. It happens in submarines. Submarine propellers go very, very slowly. The reason for that is that you don't develop very low pressures on the surface of the propeller blade. It cavitates, it makes a bang, and you can hear it, and you can be detected. And so we'll use the ideas of that also as we go through here. Okay, so I won't say much more about pressure other than the fact that this distinction between liquid and vapor is the important distinction. It's really the vapor pressure boundary, and that's what we'll use to be able to look at these. We should be at, I'm going to stop now, we should be at 15 minutes. I think we're a bit more than that. Let's go back to here. Things are still going on. We can make this a full screen. The breakwaters being breached. The one thing which is interesting in this is that, people think of tidal waves, tsunami. Actually, I think it directly translates to harbor wave. The Japanese word means harbor wave. People think of it as a breaking wave that crashes over a boundary and inundates everything. Actually, it's a very slow, creeping rise in tide that occurs maybe faster than you can run if you're on a flat-lying beach, but doesn't occur so quickly if you're in an area of land that rises quite steeply. So here you see this inexorably coming in. It's drowning some of the port facilities, as you see here. And we're 20 minutes in. We said something like it should be 15 minutes to go 100 kilometers from offshore, and that's exactly what you see it doing here. All right. Let me put that back in the top right-hand corner and deal with the very final thing that we should talk about today, and that is the vinometer. Let me play a different movie. The vinometer. So when you're out on Thirsty Thursday and you want to see what the alcohol content is of your beer, or if you're with friends and of course you can't drink because you're still 20, you can put it in a vinometer. Vinometer is just something that gives you the alcohol content of liquids. And so what you do is you put the liquid in here. If I had water, I'd put it in. It fills up this little capsule at the top. This is a Capri tube, which has, you can see the hole through it, which comes out of the bottom. You blow until water comes out of the bottom, so you fill up this Capri tube, and then you stand it upside down. You stand it upside down, and now this is open, and you can look within this tube, it's graduated on the side, to give you the alcohol content, which is the height to which this will stand up within this tube. And so it's really controlled by the surface tension, which would be across the top of this tube, open at the bottom here, which is at atmospheric pressure. And so it's a direct analog to the system that we'll look at right now. That's the end of that movie. All right, so the final thing that we'll talk about today is surface tension. So we've gone through these 3 plus, and this is the final fourth, is surface tension. And maybe we'll just do that. I'll do this on a diagram. So you still have Kamaishi going in the background. You can see that. Don't get too distracted. You should be, I don't know if you like multitasking or not. So surface tension is the mechanism by which bugs are able to walk on a surface. And the idea is if you have a Capri tube and you dip it in water, then you get a certain height rise of the fluid along that capillary tube, which we'll call H for a given diameter. So it's just like the venometer we looked at, but kind of backwards. We're pushing this tube into water. There's a height rise that occurs in here. We know that from we'll look about fluid statics that if you can connect these 2 points, both on the surface of the water here, which must be at atmospheric pressure, and in here, that's at the same level that also must be at atmospheric pressure, then basically what we can do is we can cut off this column of fluid, which is given here, which is on the inside of this tube. And we can look at a free body diagram which describes this behavior. And the free body diagram is that there is a weight of this that's pulling down, and around this periphery here we have a tensile force which is pulling it up, which is just from this contact that occurs at this boundary that we have right here. There is an angle here which we'll call alpha. And so if we do a free body diagram, the forces acting upwards are due to surface tension, and they're equal to the interfacial tension times the circumference, which is pi d. And it's multiplied by the cosine of this angle, because we want the vertical component, which is t cosine alpha. And pulling down, we have the weight, which is equal to the density times the gravity times the volume, which is equal to the density times the gravity times pi d squared upon 4, multiplied by h. So this term is just equal to the volume of this thing here. If we equate these together, because they have to be equal to each other, then we end up with interfacial tension pi d cosine alpha is equal to rho g pi d squared upon 4 times h. And we can get rid of some things. We can get rid of pi's. We can get rid of one of the d's. And if we rearrange things in terms of h, I'll just move this up. We find out that h is going to be equal to interfacial tension, the cosine of alpha of this inclination, divided through by rho g times the diameter, and 4 goes on the top. And so this says that the height rise that we get in this system is going to be proportional to the interfacial tension. This is the surface tension. So sigma is equal to surface tension. A material property. It's something like, well, let's not worry about it. And it's inversely proportional to diameter. So as the diameter gets bigger, the rise up the tube will be less. As the interfacial tension gets larger, the rise up the tube will be larger. And so we can use that to understand things like the venometer. So what's going on in the venometer is that the height rise within the tube is proportional to the magnitude of the interfacial tension and inversely proportional to the diameter. It has a given diameter that doesn't change. So what it's saying is that if you're able to look at the different height rises within that tube with different alcohol contents, it's making the case that there's probably two corresponding effects that influence the behavior. One is as you increase, we know that the interfacial tension of alcohol is not equal to that for water. So in other words, having a mixture of the two would give you an interfacial tension that's maybe proportionate to the two interfacial tensions of the two fluids, as a simple way of doing that. But also the density of alcohol is less than water. And so since both the density and interfacial tension play in this expression that gives you the height rise, if you know how the density and interfacial tension of mixtures of alcohol from 0% to 70%, say, affect these two coefficients, you can calibrate it for what the alcohol content is directly with the height rise. Basically how it works. And so that's how it is. So what's going on in the clip? Well, I think we've got a bit of mayhem going on in the clip. And so by now, this tidal surge has completely filled up the river that goes along behind this. The town was previously guarded by a wall, just like the Fukushima plant was. The wall wasn't tall enough to be able to rebuff the rising tide, and therefore it has been overrun. Okay. So anyway, so have a look at this at your leisure. So we are through. Congratulations, you've survived the first week in this class. Hope you're having fun. I'm having fun. It's a multi-sensory experience, as you can see. Live now and able to do these things are the first assignments, due next Thursday at midnight. You have enough information to do it. For those who came in late, the TA hours are on the revised syllabus online, and so if you want help, you can find help there.